We now take a look at a very important application of first order differential equations, and it is referred to as Newton's law of heating or cooling. And let me describe how the problems sort of arise, right? So let's say, and it can show up in two ways. It could be a situation where you have a warm environment, and in that warm environment, you place an object that is much cooler, right? And then, so let's say, this is and we're measuring the temperature of this object. Well, the moment I put this cooler object in a warmer environment here, the temperature will increase, right? And similarly, if I have a relatively cold or a colder environment and I put a warmer object in that environment, then its temperature will decrease. So it's like, for instance, taking something that's warm or even room temperature and putting it, or I should say something cold. You take something right out of the freezer, your leftovers, and then you put them in an oven to heat up. Or this could be a situation where you've just taken something from out of the oven and then you put it on your counter and with the hopes that it will cool. So in this situation, the temperature will go down, it will decrease, right? But then the rate at which the temperature may increase or decrease, it depends on a lot of variables, right? It depends on, for instance, how great is the temperature difference between the object and the surrounding, right? Well, Newton figured out, with probably based on some empirical evidence and then some mathematical confirmation, he figured out that this was going to happen. So it says the rate at which the temperature of an object changes, right? So at what rate does that temperature increase or decrease? Well, that rate is proportional to, the difference between the object's temperature. So let's say the temperature of the object and the temperature of the surrounding medium, right? So, and the temperature of the surrounding medium. And that temperature of the surrounding medium, meaning it could be air, it could be, water. This temperature of the surrounding medium is called it's often called the ambient temperature. Right? And the temperature of the medium, the surrounding medium, it could be constant, like in a well-controlled environment, or it could be a variable, right? You could be outside in nature, and it's hotter during the day, obviously cooler at night. So this temperature of the surrounding medium could be constant or variable, right? But this is Newton's law, right? Again, let's restate what the law says. The rate at which the temperature changes is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. So what this is saying is the greater the temperature between the blue and the red, right? The greater the difference in the temperature between the blue and the red, then the faster this thing will heat up. And similarly, the greater the temperature between the red and the blue in this situation, the faster the temperature will cool, right? Or will decrease. So let's see if we can get a differential equation out of this. So we need some variables. So it's probably not the best use of variables, but we're going to use big T for temperature and little t for time. So we're going to say let T of t represent the object's temperature at time little t, right? So big T, the temperature, is going to be a function of time, right? And let's also come up with, so the temperature of the surrounding medium, we can use something like, these are the symbols that are typically used. So like your T sub m for the temperature of the medium, or it might be T sub A for the ambient temperature, or it might be T sub E, where it's temperature of the environment, the surrounding environment. So any of these can be used to represent the temperature of the medium, right? So this is the temperature of the surrounding medium. And as I stated earlier, it could be a constant, or it could also be a function of t, little t, that is. All right, so let's see what it says. Let's start out with this, the rate at which the temperature of an object changes. That is referring to the derivative of the temperature. So let's write that down. So the derivative, so big T with respect to little t, right? So that's that part, is proportional to, so this part here, well, we're just gonna, we have the symbol for proportionality, right? So the rate of change of our temperature with respect to time is proportional to, and it says the difference. Well, the difference is a subtraction. And it says the difference between the temperature of the object, well, that's big T. So I'm going to put my big T there. And the temperature of the surrounding medium, right? So we're basically looking at all of this is what we're going to write down on the right-hand side of our proportionality, right? So the difference, there is the minus, temperature of the object, there's the big T, and then the temperature of the surrounding medium, that's our T sub, and let me just use T sub m, right? So temperature of the medium. So that's what Newton states, right? And that's not to say this is the only temperature law, but in many instances, this law is actually, it represents a very good mathematical abstraction of something physical, right? So then let's actually make this a differential equation. So we can say d big T with respect to d little t is equal to k times t minus tm, right? And this is our formula, right? And we know that k is the constant of proportionality. So where k is the constant of proportionality. All right, and that's it. So a very simple formula. And the nice thing about this is that Newton's law always leads to a linear differential equation. So this is always linear, right? Even if the temperature of the surrounding medium is not a constant, it will only be a function of time, little t, right? So as far as where big T will show up in this differential equation, it's going to be here in the derivative, and then it's going to be here in the, again, the temperature of the object. So what's nice is it is linear, and also notice that it's separable as well. In fact, it's autonomous. In fact, let's list all the different classifications of this. If our temperature, okay, so let me say this, without any other, actually, now that I think about it, the only thing we can say for sure is that it's always linear. Depending on the temperature of the medium, it might also be separable, and it might also be autonomous, right? So let me state this here, and then obviously once we go through our examples, we can then further classify the differential equation. But the fact that we know that it's always linear, it means we can always attempt to solve using integrating factors, right? So let's go ahead and do a particular problem, right? So let's look at an example. So suppose an object whose current temperature is, so let's say it's like 40 degrees, right? Is 40 degrees, is placed into an oven whose temperature is maintained at let's say 300 degrees. So 300 degrees, right? If at t equals 1, so so t equals 1, the temperature of the object is now, let's say, what will be a good temperature like a minute later? Let's say 85 degrees, right? So it went up 45 degrees. Oh, well, actually, let's double this and say 2 minutes later, the temperature of the object is now 85 degrees, right? Find the temperature of the object as a function of t, right? There we go. So let's see. So we're gonna write down what we know. So we're gonna assume Newton's law, right? So let's start with the differential equation. So that part's a given, right? In fact, all of this is pretty much a given because we don't know what the temperature function is. In fact, that's what we want to find. We don't know what the constant of proportionality is in general. And then minus, but let's see, since the object is being placed in an oven where the temperature is set at 300 degrees, that's going to be the temperature of the surrounding medium. So we got 300 there, all right? So that's the differential equation. Next up, but there was some other information given. It says that the object has a current temperature of 40 degrees. So that would be like the initial temperature. So that's the temperature of the object the moment that it's placed into this oven. So that means the temperature at t equals 0 is 40 degrees. And then let's say it's minutes, 2 minutes later, so then the temperature, or if you just want to say 2 units of time later, the temperature of the object is 85 degrees. So there we have two conditions. Why are we going to need two conditions? Well, we have a constant that we're going to have to solve for, constant of proportionality, plus once we solve the first order differential equation, we're going to get another constant, a constant of integration. So we're going to need these two bits of information to solve for k and c after we get to it. All right? Now, this one, now that we know what the temperature of the surrounding medium is, it's a constant 300 degrees. This differential equation is linear. This differential equation is separable. And it's also autonomous because on this side now, I don't have my independent variable little t. So this is also autonomous. Now, the fact that it's autonomous doesn't really help us because if we were to treat it purely as a qualitative problem, then there's only so much information we could obtain. But since we want to find the actual function for our temperature, right, like what is the temperature at any given time, usually greater than or equal to 0, then we wouldn't use this, right? So then that leaves, we have a choice. Now with the separable differential equation, then you have two integrals and you have a bit of algebra that's often necessary to get it in an explicit form. So I'm gonna maybe put a question mark there. I am going to attempt to do it as a linear problem first and see what progress we make, right? Okay, so in order to apply the integrating factor method, then I have to write this in the standard form, right? Which means I have to get the derivative and the unknown function on this side and then identify coefficients. So in order to do that, let's go ahead and distribute the k. So if I distribute k, I'll get k times t minus 300k. So let's go ahead, and if I subtract the kt from both sides, I will have this equals negative 300k. All right. Okay, so that's not too bad. Here's our p. Remember, p is whatever object is multiplying our unknown function. And in this case, it's negative k. So I'll write that p of little t is negative k. And then this is my q on this side, right? So q of t is my negative 300k. So once I've identified p, then I can find my integrating factor. So that's e to the integral, in this case, of negative k with respect to t. So since k is a constant, we will end up having e to the negative k times t, right? So that's our integrating factor, and then we use our procedure. We're going to multiply our differential equation, both sides of the differential equation, by e to the negative kt. So it's e to the negative kt dt d little t minus k e to the negative k little t times big T is equal to negative 300k e to the negative kt. All right, so that's what we have, and let's look carefully to see if we have our pattern for the reversing the product rule, right? So there's my e to the negative kt, and look over here, I have its derivative. All right, it's the derivative based on the chain rule. And that's why I have that negative k multiplying the exponential, right? So if this is my f, then this is my f prime, and then I can see what's left. If this is my g, and then there is its g prime, there is its derivative. So yes, it still works even though I have essentially an unknown constant. The pattern is still there. So that left-hand side becomes the derivative with respect to t of our integrating factor times our unknown temperature function. And then we'll bring down this function on the right hand side. And then since we're solving for big T, let's go ahead and take the antiderivative of both sides. So I'll get that e to the negative kt times t is the integral of negative 300k e to the negative kt with respect to t. Now remember, k is being treated as a constant. So as far as where we have constants in this expression, this is a constant, and obviously that is a constant, right? So don't overcomplicate this integral. What we get is e to the negative kt times big T on the left, and then over here, say we would factor out the negative 300k, right? But then when I integrate the exponential function, I have to divide by the constant that's multiplying the t. So I'll have to divide by negative k, and the exponential function stays the same, but we have our plus c, right? So this actually simplifies nicely because the negative sign goes, the factor of k goes, and I'm left with e to the negative kt times t is equal to 300 e to the negative kt plus c. All right, so there we go. And if we wanted to, we could actually, since it's just a matter of dividing through by the exponential, we could go ahead and divide by the exponential function e to the negative kt and get that. So let me write this down now. So here's our temperature as a function of little t. It's 300 plus c e to the kt. And notice I changed the sign of the coefficient of t in the exponent because I'm dividing both sides by e to the negative kt. So then applying our properties of exponents, when we take the reciprocal, we get e to the kt. All right. So, and this would be degrees. In fact, it's degrees Fahrenheit, which I didn't state earlier. But there we go. But this is the general temperature function. We want the one that's specific to this scenario. So this is where we get to use our initial condition. So let's start with the temperature, the moment it's put into this oven. So when little t is equal to 0, big T is equal to, what did I say, 40. So we end up having 40 is equal to 300 plus c times e to the 0. And so that means c is 40 minus 300, which is negative 260, right? Good. So we got this is our constant of integration. Now we have to find our constant of proportionality. So we're going to have to solve for the k that's in this exponent. Well, that's where we need the remaining condition. So when t is equal to 2, the temperature is now 85 degrees Fahrenheit. So we put a 85 there. We still have our 300. We now know what c is, so I should actually just go ahead and make that a minus 260. And then I have e to the, now t is 2, little t is 2, so the exponent is 2k. So let's see, so subtract 300 from both sides, and that will give us a negative 215 is equal to negative 260 e to the 2k. Divide both sides by negative 260. So we have negative 215 divided by negative 260 is e to the 2k. And obviously the negatives go away, and let's see, this reduces to 43 over 52. That's our e to the 2k. And then take the natural log of both sides. So we'll have that 2k is the natural log of 43 over 52. Therefore, K is 1/2 the ln of 43 over 52. All right, so there we go. Okay, so now that we have the constants, I'm going to plug these constants back in. So I am going to take my -260 and plug it there. And then I'm going to take my 1/2 ln of 43 over 52 and plug it right there. And we're going to use some nice properties of exponents because we should be able to, right? Because we're going to have an e and an ln. We just have to use our properties carefully. So this implies that our temperature as a function of T is 300 minus 260, and then I have e to the 1/2 ln, let's see, so ln of 43 over 52, all of that times T, right? Now, we know the E and the ln should cancel out. There should be some simplification that happens, but it can't happen until we bring up this 1/2, right? So now there are a couple other things that we can do. So let me do this. Let me see the best way to do this. So we have our temperature. So we have 300 minus 260. So if I bring up the bring up the 1/2 and make it an exponent of the ln. So this is e to the ln of 43 over 52. So this is raised to the 1/2 power, and then all of this is multiplied by T, right? Now what happens is, because see what I have here, I have E raised to a certain power, and then that power is multiplied by another expression. So what I can use is I can use this property of exponents and say a to the mn is equal to a to the m to the n, right? So if we look at it, then this is what we will have. So so basically what I can do is I'm going to multiply the 1/2 and the T. Let me see if that's, I'm trying to think if that's the best way to interpret it. Yeah, so we can write it like this. There are several ways you can do it, but this is 300 minus 260 times, and then we have the e to the ln of 43 over 52, all of that raised to the t over 2. There we go. So I just wanted to write it in such a way that you can see what cancels out and what gets left, and you have to make sure that the correct expression ends up in the base, and then the correct expression ends up in the exponent. So here's our final answer. So our temperature at time t of this object is 300 minus 260 times the quantity. Now this is where the exponential and the logarithmic functions cancel out because they're inverses, and we have 43 over 52 to the power t over 2, and then this would be the units here would be degrees, right? So now we have this exponential function, and if we wanted to, we could do lots of other things. We could find out what the temperature is, 4 minutes after it was placed in the oven, or we could figure out how long it would take for the temperature to get to a certain point, to like 150 degrees or 200 degrees, meaning the temperature of the object, that is. The temperature of the oven, in this case, is being kept constant, right? So that is, I think, a good example that illustrates what it's like when you're working with Newton's model for heating and cooling when you have the environmental temperature being kept constant. So hopefully you found that interesting, and I'll see you in the next video for some more applications.